Yeah, great, great. So we're you know, the first thing we talked about is sequences, right? You have these numbers, A1, A2, A3, blah, blah, blah. And the reason we're interested in sequences and series is because we're interested in summing we're interested in making these infinite sums, right? We would like to be able to add up an infinite number of numbers, right? And the way we do it is we say, A sub n equals some limit if its sequence of partial sums converges to L, right? So the first thing we learned about was, convergence of a sequence, right? Convergence of a sequence. The second thing we learned about is basically the convergence of a series, which was convergence of a particular sequence, right? Convergence of a series was basically the convergence of a sequence of partial sums, S sub n, where S sub n is the sum of the first n guys, right? Okay, and then we talked about non-negative series, right? Just to remind everybody what we were doing. We talked about non-negative series, and we developed a whole bunch of tests, right? We have this whole bunch of tests for these guys. There is the, what are the tests that we developed? Can anyone remind us of what tests they were? Does anyone remember? Ancini, how about you? Do you remember any tests? What were they? No idea, really? Gisela, how about you? Just name comparison test, right? The most basic one was the basic comparison test, right? Any others? Auntie, you really have no idea? All right, go ahead. What else? She just showed you one. The root test. Okay, so that was later on. We did the root test. We also did the ratio test. We also had the limit comparison, right? Limit comparison, right? Ratio, root, right? And right. And then we talked about just general series, right? General series, and the trick here was that take absolute values, right? Take absolute values. If the sum of the absolute values converges, then your series converges. Right? And so this trick meant that whatever series you have, you can try all of these things on it, right? You can take your series and then take its absolute value, and then you've got non-negative series. And you can try all of these tests on the absolute value, on the sum of the absolute values. Okay. Although sometimes that makes you lose some information. Okay, because sometimes the absolute value diverges, but the actual series converges. Okay, and then there was one last thing that we did, which was called alternating series, right? And for this, we had something called Leibniz's test. Leibniz's test, which said that if you have an alternating series, right, you have -1 to the n, a sub n, and a sub n are all positive and going to 0, then it converges. Right. Okay, so that is basically a quick summary. I forgot one. There should be one here, the integral test. very, very useful test. Okay. It's a quick summary of all of last week, I would say, except for the exam. Okay. Okay. So we have all these tools now, right? We have all these tools that allow us to check whether a series is divergent or convergent. Now comes the final game. Okay, the last game is so-called the game of power series. Okay, so we are going to create these things which are basically like infinite polynomials. Okay, and so they are going to be things like this. It's going to look like this: a sub n, x to the n. Okay, and it'll be a function. Let's call it p of x. A sub n, x to the n, where a sub n are your constants, right? These are the coefficients, and the x is your variable. Okay, the x is your variable. Okay, so you're creating functions now, and this is some infinite. This is some infinite series. Okay, so instead of just summing a bunch of numbers, you're throwing in a variable, right? You're throwing in a variable. The numbers are the coefficients of the powers of your variable. Okay. And so as your x varies, right, as x changes, you're going to get different series. Okay. Okay. So let's make this a definition. A series of the form of this form, and maybe I'll leave out the name. I'm not going to give it a name, but a series of the form blah, where the a sub n are these coefficients, and then x is a real variable, is called a power series in x. Power series in x. Okay. Similarly, and this is sometimes called centered at zero. Centered at zero. And that should be sort of mysterious right now, but we'll make it clear why it's called that in a minute. Okay. Similarly, a power series of the form a sub n x minus a to the n is called a power series in x minus a centered at a. So that's part one of the definition. Second part of the definition is given any power series, the set. I'll have to switch back to the blue marker. The set of C such that a sub n, c sub n converges. Oops. It's just called the domain of convergence. Okay. And later on we're going to call it the the disk of convergence, or the interval or disk of convergence. Okay, but right now we're just going to call it the domain of convergence. Okay, so let's give an example. Okay, the most simple example is this one: summation x to the n from 0 to infinity. Okay, so here's a power series. Right. Maybe the simplest power series. All of the coefficients are the number 1, right? All of the a sub n are 1. Yep, right? This thing here, you think of as a0 plus a1x plus a2x squared plus ... This one is just 1 plus x squared. Right? This is 1 plus x squared plus. Sometimes people write it out like this. Sometimes people write it out like this. What they really mean is this. Okay, so this is a power series here, right? If you put in different x's, you get out different answers, right? It's a function of x, right? If I put in a half, what do I get? Suppose x is a half, then this is going to be 1 plus a half squared plus a half cubed plus a half to the 4th, etc., etc. What's the value? You should know. Right? What's 1 plus a half squared plus a half cubed plus etc.? It's 2, right? You know it. This is a geometric series, right? Okay. Well, okay, so, right, and if I put in, say, 1, what do I get? What if I let x be 1? Then what's the answer? What's the sum? Won't be. How about you? What's the answer? If I put in 1 here, I get 1 plus 1 plus 1 plus 1. So what is that? As n goes to infinity, yeah. So you let n go to infinity, and you get. Well, I mean, this is a geometric series, but the number you're putting in is 1, right? So, you know, is this convergent? If I have 1 plus 1 plus 1 plus 1 plus 1 plus 1 plus 1. Is it convergent? No, it's not convergent. Right. So you get nothing actually, but it's divergent. Right. Okay. So what I'm trying to the point I'm trying to make here is that, you know, if you put in a number, you know, it depends on the number that you put in whether or not there's an answer, right? And what you see, so what's the domain of convergence? Who can tell me what's the domain of convergence for this power series? Here's a power series. What x gives you a convergent series? That's unique. What? Say it a little bit louder. I can't hear you for some reason. Smaller than 1? What? Yeah. So the absolute value has to be smaller than 1, right? The absolute value has to be smaller than 1. Your translator. I see. Yeah, it has to. The absolute value is smaller than 1. Right, so this is the interval. This is the domain of convergence, right? Negative 1, 1 is the interval of convergence, right? And what we saw earlier was that, you know, this was the geometric series, right? What we saw was that, you know, for x in this interval, summation x to the n is going to be 1 over 1 minus x. It's going to be 1 over 1 minus x. And then whenever you're outside that interval, then you get, it's a divergent series. Okay. Anyone confused? Anyone confused? Wang Qingchang, do you have questions? No? Okay, good. Okay. So, right, so we have this thing called the power series, right? And we have this thing, the interval of convergence. Here's an example. Here's a power series. This power series makes sense only for x between -1 and 1. Right? Anywhere outside of there doesn't make any sense at all. Right? You just get infinity, or it doesn't converge. Right? If it's -1, then the partial sum sequence just bounces back and forth. Okay. So I'd like to make Wang Di, which one of this? Okay. So here is this. So look at this. Here is this function, right? And then you have an expression for it, right? 1 over 1 minus x. 1 over 1 minus x actually is this infinite series, right? 1 over 1 minus x is a function, and here you have an infinite series that expresses it. You have an infinite series that expresses it. But here's something strange, right? So something strange. Which is that 1 over 1 minus x makes sense on all of R, right? 1 over 1 minus x makes sense on all of R, right? But this thing only makes sense with between -1 and 1, right? So, but 1 over, x to the n converges only on -1. Okay, so just an observation to make at this point. Okay. Okay, and another observation we make is that -1, 1 is centered at x equals 0. Right? If you look at -1, 1, right, then the middle of it is 0. Okay. And that actually will turn out to be something that happens all the time. It's not a coincidence that this happened. Okay. It's always going to be centered at some, and for these guys, the set of convergence will always be centered at A. For these series, they will always be centered at 0. So okay. So I'm gonna have to make some sort of theoretical statements right now. Be patient. So here's the theorem about the integral, the form of the domain of convergence. Okay. So let summation c sub n x minus a quantity to the n be a power series then its interval of convergence must be of the following form. Must be of the following form. It could be the whole line. Right. So there are basically going to be three possibilities. Either the interval of convergence is the whole line, or the interval is just the point A. Okay. Or the interval is an interval centered at A. Centered at A. Okay. It could be open, or closed, or half open. It could be one of these three things, but it has to be one of those three things. Okay, so you can't, if this is A, you can't have an interval of convergence that looks like this. You can't have an interval of convergence that looks like this. It has to be centered at A, right? It'll be centered at A. It'll be like A plus delta, A minus delta. Okay, it could be an open interval. It could be a closed interval, A minus delta, A plus delta. Or it could be a half open and half closed interval. Okay, so it could be any one of these things, right? It could also be this way, right? But it's either a single point or the whole line, or it's an interval of one of these forms centered at A. So these are the only possibilities. Must be one of the following forms. Okay. So I'm not gonna really explain this one. I'm not gonna explain this too much, but it follows from a particular fact. Okay, so this is the crucial. This what we're gonna say now explains why this happens, basically. If summation a sub n x to the n is a power series, and C is not equal to 0, if the series converges at C, then it converges absolutely in x minus C. Yeah, okay, good. Great, thanks so much. If it converges at, so if, so if the series converges at C, then it converges absolutely for all for all x such that absolute value of x is less than the absolute value of c. Okay. Second fact, this is actually the same as the first fact. If it diverges at C at some x, then it diverges at all C such that the absolute value of C is bigger than the absolute value of x. Let me give an example. So let me give the picture. So here's the picture. Okay. So you have some power series a sub n x to the n. You have some power series a sub n x to the n, and here is 0. Okay. What this is saying is that if you check one point and it happens to converge there. So suppose you check this point C, okay, and you find out that your series converges there. What that tells you is that for everything of absolute value smaller than the absolute value of C, from here to here, you have absolute convergence. Okay, just getting that one point at C gives you convergence on this whole range. Okay, so if I checked some point like -5, and I found that I have convergence there, that would tell me that between -5 and 5, I've got absolute convergence there. Okay, so if I check 10 and I get convergence there, that tells me that between -10 and 10, I've got convergence. Okay, so you see why this fact ensures the symmetry, right? This fact forces the set of convergence to have this symmetry around A, right? I should say that similarly for x minus for series C sub n x minus a to the n, right? So if you have, suppose this is A, and you get convergence at A plus C. If you get convergence at A plus C, then you get absolute convergence from A minus C all the way to A plus C. Okay, so if you get convergence at this one point, that gives you absolute convergence on everything inside. Okay, so that's what the lemma is saying. You guys, is it making sense? Even if you don't understand why it's true, does the statement make sense? Okay. Anyone have a question? Yeah. Shijun.
Why do I have to say if the series is a power series, isn't any series in that form a power series?
Oh yeah. So you could just say let blah be a power series. How's that? That's better? Or let given a power series blah. How's that? Okay. Yeah, that's you're right. It makes it sound like there's a chance that it might not be a power series, but this is a power series. You're right. So maybe this is more precise language. Yeah. Okay. So I hope everybody is seeing I hope everybody understands the statement of this lemma, and also that you see how the lemma forces the domain of convergence to be symmetric. right? Because whenever you have a point of convergence, you have this full symmetric set of convergence, right? Right. Okay. So, right. So this is really a statement about symmetry. Although it doesn't have to be perfectly symmetric, right? You could have convergence here, but not on the other side. Okay. But roughly it's symmetric. Okay. Okay. So let me give an example. Okay. So summation, say, negative x quantity to the n over n from n equals 1 to infinity. Okay. Okay. So we saw earlier that we saw earlier that negative 1 to the n over n from n equals 1 to infinity converges. Right? We saw that earlier, that negative 1 to the n over n converges. Right? This was the alternating harmonic series. Right? And we did by using Leibniz's test, also called the alternating series test. Okay. So what does that give you? So we know that this power series converges at 1. So what does that tell you? Go ahead, Francine. From negative 1. Yeah, we know that because we know it converges at 1, we know that it converges from negative 1 to 1. Okay. So at this point, what we know is that this is 0, this is negative 1, 1. We know that it has convergence here, and so that gives us convergence on from negative 1 to 1, right? Right. So at this point, what we know is that from negative 1 to 1, the series converges. Okay. What about at negative 1? What about at negative 1? Does it converge at negative 1? Suppose we put in a negative 1 here. Suppose we put a negative 1 here. Think about it for half a minute, and then I want you to talk to your friend about it. Talk to somebody in your class. Okay, talk to somebody next to you and say, this is what happens at negative 1. Okay, who can say something about it? Zhang Dongze.
It's convergence.
It converges? Okay, are you saying that if I put in, here I've got this negative x to the n over n from 1 to